then some reactions with double bonds. So that's kind of exciting. Alright. Let me just make sure. Alright, and this is on your chapter 13 handout, this picture. So last time we talked about a constitutional isomer, a molecule that differs in the way the atoms are bonded to each other. So there we gave an example of propane with a bromine atom bonded on the end or in the middle. That's a constitutional isomer. The atoms are connected differently, but we have the same formula. Okay. The other type of isomer is a stereoisomer. It's only different in the 3D arrangement, but it is different. It has different chemical properties, it has different physical properties, but it has the same chemical formula and it has the same bonds. It just differs by the 3D shape of the molecule. So if we look at these two here, these two molecules have the same formula, but they have different connectivity. If we look at this one, there's the double bond in the middle. This one, we have one butene, the double bond is at the end. But if we look at these two, this is what we're going to talk about today. We have cis isomers and we have trans isomers. And so we're going to talk about what that means. And that is a stereoisomer. So the double bond is both at 2, but the methyl groups at the end are either on the same side, that's cis, or they're on opposite sides, that's trans. Okay. 1 second. Yep.
Let me go back. Just,
oh, yes.
I'm sorry.
No, that's fine. Oh, did I? Oh, I didn't realize that I. Here?
Yes.
I didn't realize that I had found it, sorry.
It's just, I couldn't find this on the last slide. Like, definition somewhere.
Okay, yeah. The pictures, yeah, just the pictures on your handout.
Okay, thank you.
Yep. All right, so cis means that the longest chain carbon is on the same side. So here, this is oleic acid. Have you guys heard of this? I don't know where it is found, but if this is a cis isomer, then our largest groups are locked onto the same side. Remember that because it's a double bond, our molecule can't rotate. Our molecule can rotate around all of these other single bonds except for this one. And this isomer is locked where both of the longest chains are on the same side. So that's a cis isomer. Okay.
So, what do you mean on the same side?
So this would be like the top and this is the bottom.
Gotcha.
Yeah.
Okay.
So if one group was up here,
gotcha,
then that's a trans isomer.
Okay, thank you.
Yeah, good question.
Could it be, like, both could be at the...
Both could be at the
that one?
top. Both could be at the top or both could be at the
What
bottom.
if they're like this?
Then, like if you rotated your molecule?
No. You kept the double bond there and it just had the one carbon and the hydrogens over here and then on the other side.
That would be
Does
trans.
that make sense?
Yes, that would be, I think that would still be a trans isomer,
Okay.
I think.
Okay. Thank you.
But that's not across the double bond. That's on the same carbon.
Yeah.
So then you would have to look at, I don't know why this is moving. You would have to look at what else is bonded to it. So if this was just hydrogens, I will think about it. I think they have to be on the opposite carbons.
Okay.
So if you put another group up here, that would be on the same carbon, not the opposite carbon.
Okay.
Yeah, good question. Okay, and then a trans isomer. So here is that version of the trans isomer. So trans isomers are generally, we think of them as like flat because we're going along our chain and then we go from the double bond across the double bond and then back down. So if it's a cis isomer, then it's usually a bent molecule. That creates a bent. So a trans isomer, it can't rotate around the double bond. So we have one big group on one side, another big group on the other side. Okay, and then last time we talked about saturated hydrocarbons where they don't have any double bonds or triple bonds. They just have all hydrogens. That's a saturated hydrocarbon. Okay,
So wait,
oops, yeah.
sorry.
No, you're fine.
Where's the double bond in this case?
It's here, and then it's really hard to see because this is called the space filling model.
Okay.
So it would be right here. And the double bond's right here.
So the double bond would be like, if it were drawn how our last one was, it'd be like down here and then up here, right?
Yeah, yeah. So, or just like zigzag, zigzag. So this one's on the top, this one's on the bottom.
Okay.
This one's on the bottom, this one's also on the bottom of that double bond. And then the last one has no double bond. Okay, oops. Where's the mouse go? Okay, so this is more of like what we will see. So those molecules are more applicable to like cell biology. These molecules would be something you see in a biology or a biochemistry class. These are more of what we're going to see. So we have 2 carbons in a double bond. We have these 2 methyl groups on either of the carbons participating in the double bond, and they are on the same side of the double bond. And then over here, we have these 2 carbons participating in the double bond. One has a methyl bonded up here, one has a methyl bonded down here. And because we can't rotate around the double bond, it's locked. So this is locked in the trans isomer. This is locked in the cis isomer. Everything else is the same. Same formula. Same connectivity. We just have the groups are locked above the double bond or one above and one below the double bond. These molecules would have different reactivities, and that's why we care. They are different, they have different physical properties, they have different chemical properties, different reactivities. So this is why trans fats are so bad, because our body is not very good at breaking down trans fat. Our body can handle cis fat pretty easily. These are pretty weak bonds. These are weaker bonds than a trans bond. So that's why we care about trans fat, because this is harder for us to break down. So I think that's kind of interesting. All right, so go ahead and try to draw these 2 isomers. So we're trying to draw trans 4-methyl-2-pentene and cis 4-methyl-2-pentene. So we're drawing isomer pairs. The only difference is where the groups are located in space.
How do you want us to draw?
I like drawing the stick models. If you want to draw a condensed structure, you can. The line structure. Yeah. Aim, if you say it like aim, then it's a single bond. Yeah. So yeah, YN is the triple bond. Yeah. There's no triple bonds up there. So there's just double bonds here because it's pentene. E and E is double bond. Yeah. Yeah. But however, I just like it spelled too. All right. Are you guys ready? Do you want a minute? 1 minute? Okay. I see people still working. Yes. Okay, let's talk about these molecules. Let's draw them up here. Does somebody want to come draw one of them up here, actually? Anyone? No. Okay. All right, so this is how I do this. Oh, I need to turn the other one on. So I look at this end part. It's pentene. So I just start with 1, 2, 3, 4, 5. Oh, 5. Oops. Oh, now it's gonna not work for us. This is gonna work. Oh, there we go. Okay. I'll just start over. Okay. 1, 2, 3, 4, 5. So we've got pentene. It says 2 pentene, so whatever end I'm starting from, I could start over here or I could start over here. It doesn't matter. I'm going to start here and say this is my double bond. So 2 pentene. And then it says 4 methyl. 1, 2, 3, 4. So I'm going to come straight off of this here. So now we have trans 4 methyl 2 pentene. So we need to check if it's a trans isomer or not. So across my double bond, do I have both of the carbon groups on the same side or are the carbon groups on the opposite side? So this is like I'm cut my double bond through the double bond. So one side is the top, one side is the bottom.
I'm freaking confused. So it's not like specified, but is there really like a CH3 on the like or
On
what
here?
is it? Yeah, what's it talking about that's on the different sides? Because I'm confused.
It's talking about the carbon groups.
Yeah,
So
I got that far.
across the double bond.
I got this far. But I
Okay,
don't
this is, okay, so then we're looking at our double bond. We look above the double bond.
Yeah.
And below the double bond.
Okay.
Are the carbon groups on the same side or are they on opposite sides?
Opposite.
They're on opposite sides. So this one is already trans. So then we have to make it a cis molecule by taking one of these. So I can either flip this onto the same side or I can take this group and flip it onto the same side. So it's easier to move just one group. So I'm going to take this group and move it up. So I'm going to say, and remember, it helps me to remember that these look like hexagons if we drew out all of the hexagon. So here's my double bond. And so now I still have, this is a carbon 1, 2, 3, 4, 5. So it's still 2 pentene, 4 methyl. But now if I look at this double bond and I cut it in half, there's 2 carbon groups above it, and then these would be hydrogens. If we drew them in, we would have hydrogens down here. So the smaller groups are on the same side, the larger groups are also on the same side. So this is cis, this is trans. These are the same formula molecules, they have the same connectivity. This one is just locked so that the methyl group is on the same group as same side of this other group, and the methyl group is on the opposite side of this carbon group. Does that make sense? Yes.
So like the groups don't need to be balanced. You don't need to have a methyl on both sides. I don't know what I was thinking, but I was like, I can't. It's not balanced because there's not also a methyl group.
So there is a methyl group.
Well, oh.
This one.
Oh yeah. Okay.
And this one. Does that help?
Oh yeah, I've seen that.
Okay. So let's draw it in a different color. So if we can, maybe we can't. They give me this button like it's gonna do something. Okay, there we go. Oh, now it's not going to. So here, I took that and I just flipped it above the double bond.
So you don't need to have the same amount of carbons.
It does have the same amount of carbons. So we can write it out. This is CH3, CH2, CH2, CH, CH3, CH3. And this one is also CH3, CH2, CH2, CH, and then 2 methyl groups. Okay, did that help? Okay. This is kind of confusing. Other concerns? Any other questions? Ask some questions. Okay, all right. Okay, the last thing that we're going to talk about is the reaction of alkenes. So remember, an alkene is a double bond. We're going to talk about addition reactions. We're going to talk about 2 addition reactions. So we take an alkene, some double bonded molecule. We're going to add another molecule to it. And these are pretty reactive, and we can add things across a double bond. So this molecule will split. We will get one part of the molecule on one of the carbons of the double bond, and one of the other part of the molecule on the other carbon in the double bond. So we have a double bond breaking and 2 single bonds forming. This is called an addition reaction. We're adding something across the double bond. And the 2 we're going to talk about are on our paper here. We're going to talk about just 2. There's a whole bunch. Okay, so we're going to look at hydration and hydrogenation, but these are some of the other ones that we can add. So we can have a halogenation, or we can have a hydrohalogenation, but we're just going to talk about a hydration or a hydrogenation. So if you take an organic chemistry class, you go into detail about all of these reactions and other reactions. So organic chemistry, we learn about how to name molecules, but also how do they react and can we predict their products or their reactants? How do we make a molecule? So we're just going to focus on hydration and hydrogenation. So the first one we're going to talk about is hydrogenation, and that's this first one on your note paper. So we have our double bond. We're going to add hydrogen. So if we look at hydrogenation, we have hydrogenation. And then for this to happen, we have to have a metal catalyst. Otherwise, this won't happen, okay? I think I have the metals that are most common. We'll see. My slides crashed the other day, so we'll see. Maybe that's what I lost. And then, so this bond breaks, the double bond breaks, and we get an addition of a hydrogen on each of the carbons on the double bond. Okay. So now we started with an alkene, we added hydrogen, now we're back to an alkane. No double bond. We got rid of our double bond. Now we just have single carbon-carbon bonds.
So, an alkane doesn't have a double bond, an alkene does, and then what's the one with the Y?
It has a triple bond.
Gotcha.
Alkyne has a triple bond.
Okay.
Okay. Oh, here we go. So we have to have a catalyst. The catalyst is usually palladium. So I have used a catalyst and it was palladium on carbon, and you just add it in there. And the palladium helps the hydrogen bond break apart, and then those hydrogen atoms can add into your molecule. So that speeds up the reaction. Other catalysts are nickel and platinum. So those are some common hydrogenation catalysts. And then for a reaction to occur, and for all of our double bonds to be hydrogenated, this is a 1-to-1 reaction. We need one molecule of hydrogen for every double bond that we have. So if we just have one double bond in our molecule, then we'll need one hydrogen for every one other molecule that has a double bond. If we had a molecule, so if you have a double bond molecule, if you have it's called a diene, then you need 2 hydrogen molecules for every molecule of that you're trying to hydrogenate if you have 2 double bonds. All right. So let's look at these two. So we have this diene. So this has 2 double bonds. That's called a diene. This is called a conjugated diene. If you take organic chemistry, we talk about how these electrons can kind of move through where these double bonds are. So that's kind of interesting. And then this is an isolated diene. So how many molecules of hydrogen would we need to hydrogenate this molecule? We need 1 per double bond. Yep, so we need 2. So it would be 1 to 2 for that molecule. And this one would be the same. We have 2 double bonds, so we'd need 2 molecules of hydrogen for every 1 molecule of this molecule. And we would end up with the same product here because we have the same number of carbons. These are both, what is this, 1, 2, 3, 4, 5, 6, 7. So these are both heptane.
So wait, the double bond just goes away and acts like it, or where does it go?
So
Because it belongs to the hydrogen, but like,
yep.
Where is the bond now?
So the double bond is, remember, the double bond is electrons being shared.
Yeah.
So that those electrons break. So you have like 2 electrons here and 2 electrons here. And so these electrons break, and now I can make a bond with hydrogen here, and I can make a bond with hydrogen here. I don't know what I said. Okay, does it make sense?
Yeah, I think so. In my brain.
So we have something like this with bond angles of 120 because there's only 3 groups. Then this is actually 2 electrons, so our electrons kind of shift.
So it just makes it normal then?
Yep.
Okay.
And so then we have like 1 electron here, 1 electron here, and then hydrogen can come in with its 1 electron. And then they can form that bond.
Okay.
Yep. Okay, good question. Other questions? Okay. The next type of reaction is hydration. This is where we are adding a water across our double bond. So we start with a double bond, we add water to it, and on one of the carbons we get a hydrogen. On the other carbon that was in the double bond, we get a hydroxide, OH. So for this to happen, we have to have a strong acid. So a strong acid like sulfuric acid or phosphoric acid. Otherwise, this won't work. You need a pretty strong acid for this to go. So that they call this is acid catalyzed. The acid helps this go faster. So this reaction is shown with sulfuric acid, but if you just see an H+, that means it's an acid catalyzed reaction. So the acid is not providing the water, the acid is just making things faster. And if you take organic chemistry, they will explain what exactly is going on with the acid. So this example is ethylene. We've got a double bond. One of the carbons in the double bond gets hydrogen, one gets oxygen or hydroxide. So this is a pretty simple molecule. It doesn't matter which carbon the hydrogen gets on or which carbon the hydroxide adds to. So the next slide we're going to talk about, it does matter which one it adds to. If it's a symmetrical molecule, it doesn't matter. If we flip this around, it's going to be the same product. But if we have something that's not the same, we use this Markovnikov's rule, and he found, this is called an empirical rule because he saw it experimentally, this always happened. The OH group adds to the more substituted carbon. So if there's a carbon and it has other carbon things bonded to it, that's where the OH group is going to end up. If there's a carbon with only hydrogens, that's where the hydrogen is going to end up. So let's walk through this one. So we've got propene. So we've got our double bond. We have 1, 2, 3 carbons. This carbon has a carbon and a hydrogen bonded to it. This carbon only has 2 hydrogens. So when we do our addition of water, our hydration reaction, this OH is going to bond to the more substituted carbon. And we call this is our more favored product. We'll probably get some of the other product, but this is going to be our more favored product. We're going to get the most of this. And this would be the correct answer in an Alex question. Okay, questions on that? Okay, all right, let's look at an example. So what would our products be for this hydration reaction? So we're going to get mostly the same structure, right? But our double bond is going to go away. So this, we know it's going to kind of look like this, maybe a little bit beautifuler. But we need to add an OH on one carbon that was in the double bond and a hydrogen on the other.
So would you? Never mind.
So where does the OH go?
Could it go in that middle one? Right below the CH3.
Yep, good, because this is more substituted. So OH would go here, and we would get another hydrogen. So there was already hydrogen. We have now 2 hydrogens there. Good. Okay, let's try this one. Oops, I went backwards. What would there could be a few products. A reactant. Predict a reactant, a possible reactant for this reaction.
It's just hexane with a double bond on, like in between 2 and 3, right?
Good. So we could do it like this.
What's
Just
it
like
gonna
our things.
also be between 3 and 4? Then?
Yes. So we would have a methyl group here, CH3. So we could either have this. Oops, let me draw. Yeah, we're drawing the same thing. Or we could have it over here.
Wait, where'd you get the methyl group?
Sorry?
Where'd you get the methyl?
This is the methyl group.
Isn't that just a hydrogen? We added.
No, it's because it's drawn, it's a methyl group.
So where'd the hydrogen go?
Oh, it's not in there. We don't show hydrogens.
Yeah, but where'd it go?
It's either, so you're saying like this splits up into hydrogen and OH.
Yeah.
OH is here, and we don't know. We don't draw hydrogens. So it could be here, or it could be here.
Alright.
All right, ask me a question. Or is this pretty straightforward? You okay?
Do you have any more examples?
No,
Alright.
just Alex. Okay, all right, we have about half an hour left. I would try to get through at least some of the chapter 13 Alex topics. And if you haven't turned in Lab 34, make sure you get that done and submitted. If you're all caught up, you can work on your signature assignment, or you could also work on the final, studying for the final. Okay.
Good job, Alex. Everything I did, but I totally got it.